Thank you, Paulo. Actually, the task of sort of reflecting on the work as you do the work is something that I learned from Kent Beck when he would talk about how he was doing something while also watching himself do it and thinking all the while, is this the right thing to be doing? Is there a better way? Why am I doing this? Why did I name that function as I did? So I've found that to be a useful thing to do. But it's not easy because sometimes you get more interested in the meta commentary than the actual work you're doing, and you kind of have to remember, oh yeah, need to actually finish this, get the test green, and ship it. Just a little bit about myself. I have been primarily a developer. I became an architect by receiving the title from a consulting company before I actually knew what it meant to be an architect, but it was a way that they got me in the right spot on their rate card for the client. And then I had spent several years sort of catching up to that title. I also made a move over into operations through a somewhat bizarre set of circumstances, and I ended up being the only developer on the operations team at a relatively large retailer. And it turned out, because I was a developer, I could analyze some of the failures that other people couldn't, even sometimes to the extent of decompiling code to understand why it was breaking in production. This didn't start from any noble motive. I wanted to be able to sleep through the night. Launching a new system is a bit like having a child. You expect that you're going to wake up at 3 in the morning for the first several months, but it gets old. And so I started to find these patterns of failure, and even more happily found that there were patterns we could apply to prevent those failures. That was the genesis of Release It and the second edition that has recently been released to update for a few things that have changed in the last 10 years or so. Today, I'm part of a company called Cognitect, a small outfit based in North Carolina, but really distributed. You may know us as the commercial stewards of Clojure and ClojureScript, or the creators of Datomic. I work on some of the open source contributions, which are really aimed at increasing the personal leverage of developers. Today I'm going to talk about a somewhat more general subject, though, that it's not Clojure-based. There won't be any parens in strange places to traumatize the audience. Instead, I'm going to talk about coupling and uncoupling. Because I think we've all had this experience of working in a system for a while and feeling like the parts connect just right. We've made things smaller, we've made them more independent, we've made them composable, things are going pretty well, and then somebody wants a change. You've got this beautiful arrangement, and then you get some new requirement that just doesn't fit. Maybe it's a larger bead, maybe it's a need for a gap occasionally between two other beads. Whatever it is, you start moving just one part to get ready for it. And you discover that moving that one part causes you to also change something on the other side of the world. You change that and find that something else breaks for no apparent reason. You begin to realize that your system is not this lovely arrangement of small, isolated buckyball magnets like that, but it's more like this tensegrity structure where it's all held together by opposing forces. You've got a nest of rods and ropes and some surgical tubing winding up through the whole thing, and it's actually a pile of opposing forces waiting to fly apart at any time. It's only held back from chaos by this network of interwoven dependencies that's currently fighting you. You push one place and it pushes back. You pull another piece and it moves a dozen others somewhere else in your system. And your mental view of your system changes to something more like this. Instead of the buckyballs, you're the magnet being swallowed by putty. The system fights you back. A rewrite starts to sound like a pretty good idea. After all, it'll only take a couple of weeks, right? You have fallen victim to coupling. This is the page in the Choose Your Own Adventure story that says, "Go back to page 1, you have died." It's all about coupling, and coupling appears to be the enemy. We're dissolving large systems into smaller systems. We're trying to decouple things or uncouple things wherever we can. Coupling is what fights us. It's a dirty word in our industry. We often think coupling is sort of synonymous with just bad. It keeps us from making changes, it keeps us from evolving. But in other fields, coupling is not a dirty word. It's not a problem. In fact, it may save your life. This is a Scharfenberg coupler. Apologies for my violence to the German language, to any of you who are native speakers. This coupling was invented more than 100 years ago. It's still in common use on trains, and it holds two cars of a train together in such a way that they can move around corners. It makes electrical, hydraulic, and mechanical connections all at once. This coupling provides safety. It keeps two parts together. And this is probably the reason that trains coming apart in two pieces is not nearly as much of a problem as cartoons led me to believe it would be. Other kinds of coupling perform useful tasks. This is called Watt's linkage, invented by James Watt in the steam era. It's three rigid rods connected by couplers that allow rotational movement. This arrangement of rods and couplers lets you approximate linear movement from a rotary device. This is what Watt used to drive a pump arm from a steam engine. Another arrangement of couplers gives you the Chebyshev linkage, also an approximation of linear movement. Again, three rods and couplers in a slightly different arrangement, quite different movement. In fact, in a certain sense, coupling is everywhere. In the standard model of physics, we can talk about the coupling between different fundamental particles, and that coupling is what allows them to interact and allows us all to exist. So coupling is really everywhere. When we have coupling, it determines your degrees of freedom. So if you think about those mechanical examples, the mechanical part can move in one plane, but not another. The human knee is a great example of a coupling that moves well in one plane of motion, but very bad things result if you try to move it in a different plane of motion. Some of you may have experienced this. A good friend of mine just had both knees replaced with bionic parts because they moved in the wrong plane of direction. A coupling enables some movements and inhibits others. And often it's the inhibitory effect that we grapple with in our world. Coupling between different parts of a system inhibits them from moving apart or moving separately from each other. They're forced to move together. Coupling can also connect far distant effects. And I have an example of this that comes from astronomy that I find especially beautiful. This is Saturn's moon Iapetus, sometimes referred to as the Death Star moon for that dramatic crater in the lower hemisphere. It also has a curious ridge around the equator that makes it look a little bit like a walnut. Now, this is believed to be from some impact that actually melted the crust of the moon enough that a wave was running through it and created a standing wave at the equator, with the wavelength being essentially 1/2 of the diameter of the moon. It's pretty astonishing to think about that. But the other really dramatic thing you can observe from these two hemispherical pictures is that one side is bright and one side is dark. It's hard to find a material that would create this kind of albedo difference from one side to the other. The two-tone coloring was actually discovered by Giovanni Cassini, he for whom the Cassini gap is named. So it's been observed for a long time, but we didn't know what caused it until 2009. In 2009, we discovered that the likely cause is this. This is a moon called Phoebe. It's a small moon. We didn't know it was there until a probe, the Cassini probe, was out observing Saturn. And you might even be a little condescending. I mean, Phoebe is not even big enough to pull itself into a sphere. It's this tiny little thing. 213 kilometers across. Phoebe is also far distant from Saturn. And what we've determined is that Phoebe is constantly being ablated by micrometeoroids, creating Saturn's largest ring, which also wasn't known until 2009. This ring that you can see here is 40 times bigger than the entirety of the other rings. It's so diffuse we can't observe it from Earth. That moon, or that ring, has at its outermost edge the moon Phoebe. So the material forming that ring used to be part of the moon and got blown off of it. Well, it's not too hard to do that. You could probably throw a golf ball off of Phoebe and have it go into Saturn's orbit. Over time, pressure from light itself coming from the sun acts asymmetrically on the ring material in Phoebe. Somewhat more pressure on the side that's closer to the sun, somewhat less pressure on the side that's farther away. And this causes the dust to gradually spiral inward. At this point, you may be able to guess what's at the inner edge of that ring. It is, in fact, Iapetus, which is tidally locked to Saturn, so it always has the same face forward in its orbit, and it's sweeping up the dust from Phoebe. At some point, all of the matter from Phoebe will be transferred onto Iapetus in that layer of dust. Now, these two moons are coupled via gravity and sunlight and millions of years of time. Coupling is really hard to escape. At some level, everything is coupled to everything else. Everything in your data center is exposed to ambient temperature. Everything is exposed to ambient atmosphere and even acoustic vibrations. There was a story or a report published by an online backup company that was looking at the effect of acoustic vibrations on hard drives and the failure rate of hard drives. And they actually were able to observe a higher error rate on disks that had a higher level of acoustic vibration. They controlled this and generated the acoustic vibration by putting someone in a data center, squatting down in front of a rack and screaming at the drives. Now, everything is also coupled via fields, like the electromagnetic field and the gravitational field, and even the Higgs field, which we now know to be a real thing. It would be impossible to keep track of all of these things all of the time. When I'm dealing with architecture, I don't generally contemplate which pieces are at sea level and which pieces are at a higher altitude because of differential G forces. Some of these we can neglect, and some of these we have to account for. So instead of accounting for all the things all the time, we start categorizing. We start creating a taxonomy. So when I look at coupling, I start thinking about different kinds of coupling that might bite me later on. Operational coupling is one where we have a runtime dependency among components. Some provider of a service and some consumer of a service. If the provider is unavailable, the consumer can't run. This kind of operational coupling was largely the subject of Release It and was the focus of my attention in writing that book. And in particular, finding ways to weaken or in some cases eliminate operational coupling. We also have other kinds of coupling that matter at the development time rather than at runtime. So development coupling is when you simply can't compile one piece without making a corresponding change to something else. You think about signature changes in an interface where your implementer is no longer valid because it lacks a function or it lacks a parameter. That one's not so hard. We have tools that will tell us about that. Compilers and type checkers. If you're in a dynamic language like I am most of the time, maybe the tools aren't as good and you have to have other ways of discovering it. Property-based testing, unit tests for examples here and there. Some of the other coupling is even more insidious, though. Semantic coupling is when two parts need to change because they have a shared concept. Now, this concept may or may not be directly represented as a code-level dependency. It may simply be that you have independent implementations of data structures that are meant to correspond. Oftentimes in enterprise systems, changing an entity upstream requires you to change that entity definition downstream. This is semantic coupling, and the compilers and toolchains really won't help you catch that, especially if you're in a polyglot environment. Functional coupling arises when you have multiple things that act the same because they have some shared responsibility or shared implementation. When we talk about don't repeat yourself, we're often trying to address that functional coupling, where we try to isolate one implementation of an idea such that we don't get divergence from the many consumers. And then, of course, incidental coupling is one of the worst of all. Breaking API changes for no good reason, simply because somebody wasn't aware that the API was being consumed. This has been described in Hiram's law, which says, given enough users, every implementation detail of an API will be depended on by someone somewhere. We can use these dimensions to analyze some different situations. I have a few examples drawn from Simon Brown's c4model.com, and I'd like to walk through how these different aspects of coupling, or different kinds of coupling, emerge in different kinds of interfaces. So we have a very simple example here of an email system with an email sender. Email sender is written in C#. The email system itself, we don't care. It's behind a protocol. And we have a component that's sending a notification via the other one. Well, if we look at operational coupling, it's obviously very strong. SMTP is an online protocol. It requires a connection and a conversation. It's stateful. And so if the email system is not there, the email sender is going to break. So operational coupling, very strong. The development coupling is actually pretty weak here. I could replace that Exchange server with another MTA that also speaks SMTP, and I would mostly expect things to work because we've had, frankly, tons and tons of effort put into interoperability between different vendors and different standards. If only we would get that kind of interoperability between chat systems today. I mean, Slack to HipChat to whatever, XMPP, Yahoo, who knows. The semantic coupling is very strong here. Both of these components have shared ideas of what the entity's attributes and values are. In fact, they're defined by the SMTP standard. So even though the semantic coupling is very strong, I don't worry that much about it changing, because SMTP changes very slowly. Nevertheless, if SMTP defines a new kind of header or a new kind of attribute, it would require changes in both of these systems to accommodate that change. The functional coupling is very weak here. Now remember, functional coupling is when I have similar implementations doing similar responsibilities, and they really don't have very much in common. My email sender is probably being invoked by a programmatic call inside of a single process. The job of that process is not related to the queuing, directory, spam protection, and store and forward behavior of Microsoft Exchange. And so we have a way of understanding the different aspects of this coupling and knowing which parts are concerning and which parts we can disregard. Now, suppose we're looking at another piece. Here we don't have as much of a standard, but another portion of our system is doing a SQL connection to look something up in a relational database. Well, what sort of coupling do we have here? Operationally, again, very strong. The server must be there for the consuming component to work. And even if the server has good failover semantics, has a good clustering behavior, it's often the case that the client needs to know about that so that it knows which exceptions should cause it to retry a transaction and which exceptions it can safely ignore and move on, and which ones are simply fatal. The development coupling is very strong. Depends utterly on the schema, the entities, the server version, and the protocol version. Change any of those things and you have to change both sides. Semantically, also very strong. The client has to know about the tables, columns, and what joins are legal, and the server does as well. Functionally, again, weak. There's not much shared responsibility between the behaviors of a reference data importer and the behaviors of a database server. Let's spend a couple more moments on this same interface where we have a reference data importer that needs to understand some table of information that's common to our enterprise. If we elevate it to that level, maybe we don't so much think that the reference data system has to be a database. Maybe it's a service where we use a REST-style interface instead of SQL. Well, how does that change the nature of our coupling? Operationally, it's still strong, but somewhat less so than before. If the service, or the provider side of this service, has a failover strategy, we can simply retry a REST request. We don't have to know as much about what kind of exceptions mean we can continue our work and what kind require a complete restart or a failure. Development level coupling is still strong, but somewhat less, because we have that API that represents a place where we can mitigate some of the changes to the internal structure. If we can find a micro format or some other standard representation, then we can reduce the development coupling even further. Now, I do want to make an aside. If we were looking at the database version of this, we could say, instead of directly querying tables, we'll query a view onto those tables, or we'll query a stored procedure over those tables. And that would also have the effect of weakening the development coupling, but it's still going to be there and still significant. Semantic coupling, still very strong. We have the same concepts being represented on both sides, and we need to have a mapping between them. The functional coupling, still weak. So now we're looking at how we can change the nature of the interface to achieve a kind of coupling that we can live with. But this still looks like it's pretty strongly coupled, so maybe we want to explore another option and say we'll invert the flow of control and introduce an intermediary. After all, it's a CS problem, so what's another layer of indirection? In this case, we have the reference data system publishing announcements when it changes. We have a broker in the middle that's aware of the consumers that are interested. What's our operational coupling in this case? Anyone want to throw out an assessment? What's the operational coupling from provider of the reference data to consumer being the receiver? Weak, quite weak, in fact. The receiver can even run with stale data because it's presumably got a cache or local store where it's holding on to the last known good value. Development level coupling is also weak because we have at least 2 places, and possibly 3, where we can introduce isolation from changes in the provider to changes in the consumer. Semantic coupling is still strong. After all, we are trying to transmit reference data, so there's only so much we can do in terms of abstracting that reference data into something else. But again, we have another place where we can do some remapping if needed. And in terms of functional coupling, there is some moderate functional coupling here because both of these services, the provider and the consumer, now both need to know how to talk to the message broker in the middle. And so I've introduced some shared behavior in terms of managing a connection, dealing with message semantics and acknowledgements. So in all cases, we still had coupling of various strengths and various kinds. And this is something that I think is inescapable, but it's also necessary. If you had a pile of truly decoupled services, they wouldn't talk to each other and they wouldn't do anything. And so some amount of coupling is necessary, just as those couplings in Watt's linkage allowed 3 bars to transform motion in a way that they couldn't if they were laying there as isolated pieces. Where we more often get into trouble is when we see chains of coupling knitting together systems up and down an enterprise. So we've been looking at just 2 services. But when we look at something that's more of an extended system like this, maybe it comes from a retail environment, or this one does come from a retail environment. There's often a concept like a stock keeping unit, or SKU, that ends up being sort of pervasive everywhere within systems in this same domain. Now, SKU is not a real thing. I can't go out into the wild and find a SKU laying around. You can't put a SKU on a physical table. A SKU is an abstraction over groups of entities that we think usually go together. So it'll refer to things like the display name of an item, the price and cost of the item, how much space it takes up, what kind of shipping does it take to move it from one place to another. All these are actually attributes that could be unpacked, unbundled, and represented as their own thing, tied together with a common identifier. But over time, a kind of synecdoche has occurred, where the identifier, the numeric skew, has come to stand for the whole package of attributes. In this particular retailer, they wanted to start selling a lot more SKUs, numerically speaking, of a new type. They wanted to sell digital items like skins and hats in video games. Now, digital items don't have a weight. You could put in a 0, but 0 weight doesn't really mean anything in those systems and might in fact cause a divide by 0 error somewhere down the line. They don't have any dimensions on a shelf. They have a cost, they have a price, but they don't really have a cost because your final cost depends on how many of them you sold. So the cost is computed after the fact. So a lot of things are different about these. There's also a vast number of them. And so the people who set pricing found the old means of setting pricing to be insufficient. Going into the product information management system and keying in a price works okay when you have a few hundred SKUs under your control. When you're a merchant for digital gaming and you've suddenly got 12 million SKUs under your control, you really don't want to key updates for each one of them. So they invented a new concept called the price point. And they created a relationship from SKU to price point. So you could say this price point will be 99 cents. It represents a cosmetic item for this game. And then all of the actual cosmetic items would relate back to that price point. Well, this makes perfect sense in that system. But because SKU is known everywhere, and everyone needs a SKU, they ended up transmitting this price point idea to every system downstream as well. Now, at this point, you can definitely see that there was some semantic coupling going on, and that semantic coupling caused the cost of this effort to multiply by at least an order of magnitude. Another option would have been to say price point is a concept restricted to the product information management system, and that when we export a SKU, it will have a price put on it which is flattened out from that relationship. So I'm only doing the join in one system, and everything downstream only needs to know about one concept instead of introducing this new one. When you have this kind of concept leakage through a long string of systems, I think of it as a kind of semantic polymer. You're creating this long chain molecule that can be very stretchy and elastic, but is kind of hard to move the parts independently. Another kind of coupling that you'll find in these extended systems comes from this kind of really organic diagram here. I've removed all the names to protect the guilty, but this represents a real system with no known notation or diagrammatic style, no standard represented here, and every kind of interface represented by the arrows. In fact, the architects on this project needed to make a database of all the interfaces so that they could keep track of them. And each database, or each interface in the database, had several levels of detail represented. This was level of detail 0, but if you looked at LOD1 or LOD2, you would find that each interface was really a chain of processes going on. So at the level of that first diagram, it was not useful to try and represent each of the pieces, or it would become even harder to comprehend. But one interface might, for example, run an extract into a file, move a file, load into a landing zone, ingest the items from the landing zone into the cold side of a database, and then perform a hot-cold switch so you get an atomic switch over to the new content. Another one was even longer, where you've got multiple queues, multiple wraps and unwraps involved, parsing, unparsing, processing, and reprocessing. These kind of long chain interfaces are interesting because I feel like they're sort of fractals in nature. You know, we go and we look at them, and the closer we look, the more moving parts we find along the chains. As we're looking at one of these long chain interfaces, it's interesting to find that your architectural quality of the chain is strictly worse than the worst part of each chain. So your availability is worse than the availability of the least available part. Your latency is worse than the latency of the slowest part, and so on. So it's an example where losses accumulate, but gains never do. Okay, so we've been victimized by coupling. We've tried to find a taxonomy for understanding it, and found a few places where we can look to locate it. What do we do about it? How do we get out from that blob of magnetic putty? I'm going to use an example from Parnas to illustrate this. His paper on the criteria to be used in decomposing systems into modules was the paper that introduced the idea of information hiding. Later on, Parnas said that instead of information hiding, he wished he had called it decision hiding. I'm going to borrow the illustration he did, which was this keyword rotated index. So the idea of this quick index is you take every sentence and you alphabetize it under each of the words in the sentence in these sort of rotations. So you can see the output there. It's alphabetized, and it has each word of the sentence as the leading word for one of the entries. So you can imagine it takes documentation and it explodes it out to a vast size. But it's in a very useful format if you want to do something like an apropos lookup. Now, in the paper, one gets the impression that perhaps Parnas had lost a design argument in the implementation, and he was trying to win the fight in the paper that he had lost in the team. But both of the modularizations he presents actually work. There's no straw man argument here. In this first modularization, we have an input module that reads EBCDIC characters. Some of you may remember EBCDIC. For those who don't, it was another encoding completely incompatible with ASCII. It was dominant for a while. The EBCDIC characters get read in, packed into words, and stored in an array. And then the circular shifter builds a new array which pairs together addresses of characters in the shifted form to the index in the original array. The alphabetizer does a sort. The output uses those arrays and outputs each line, and then the control module simply calls the other modules in order. Now, what's interesting here is to look at the effect of changes you might want to attempt. So imagine that you wanted to read and print ASCII instead of EBCDIC. Which modules would you have to change? Essentially all of them. Because every module was using the array created by the first one, they would all be sensitive to the character encoding. What if we wanted to stop using packed characters and store just one character per word? At the time, that would have been the most flagrant waste of memory anyone had ever heard of. But today, I mean, that's actually kind of a normal approach, right? When we're using UTF, we often do that. Again, because every module is using that index form, or using the array and indexing into the array, they would all need to change. If we wanted to use offline storage instead of core memory, same thing. Everything has to change. Parnas introduced another modularization that he viewed as superior. It started by defining an interface, this functional interface that has the ability to get a character, set a character, get a word, delete a line, and so on. Now the input module still reads EBCDIC characters, and it calls into that functional interface to store them. The circular shifter does something especially interesting. It offers the same functional interface. So now we have a defined interface and multiple implementers of that interface. It makes it appear to have all shifts of all lines. We don't know from the outside whether it in fact creates all of those shifts of all of the lines, or it simply creates an array of indices like in the first decomposition. To a certain extent, we can't know, and we shouldn't care. The alphabetizer has a different interface. It's got an init function because sorting takes a long time, and then it's got an indexed access function. And then we've got output that simply walks through linearly and prints a line. Control, very similar to the first one. Let's think about some of those similar changes. Suppose we wanted to read and print ASCII instead of EBCDIC. We actually have an option to only change the first and output modules. We can apply the transformation at the points of doing I/O. We could alternatively apply the transformation at the point of the line storage interface itself. We don't have to touch every module. Again, if we wanted to stop using packed characters and use one character per word, we could do it simply at the level of that line storage that has the get character and set character functions. And it's not hard to see that using offline storage instead of core would also be isolated to just one module at a time. And so we like the second one better because a change doesn't have as far-reaching an effect. The second one is better because it hides those decisions about how to store the characters, what representation to use, how to shift them, how to sort them. It hides those decisions inside modules. It also uses a functional interface to provide an abstraction over the data. This is what Parnas called information hiding. And I like to sort of represent it this way and think that a key aspect of what made this work is that we had very few data types, we had very few interfaces, and the interfaces were composable. So in essence, we have the line storage interface, which is offered by storage and circular shifter, and consumed by input, circular shifter, and alphabetizer. And then we have the ordered interface that lets you do the indexed access, offered by the alphabetizer, consumed by output. When you compose them into something like this, it's pretty clear how the restriction on the interfaces and the restriction on the number of data types makes this modularization better. Now we can look at each of these connectors and regard them, or look at them with respect to those types of coupling. The operational coupling is going to be high in every case because it's all running in one process. So if the consumer is not there, the producer is not there, and vice versa. The development level coupling is weakened by the use of these functional interfaces. The semantic coupling is also reduced due to using these interfaces instead of the direct access to the underlying arrays. We no longer have the shared concepts about how many bits constitute a character in an array. And the functional coupling is also reduced. So functional, again, is when we have shared mechanisms for doing similar things. In the first modularization, every module had to know how to walk through the array and find the right characters out of the array. In the second modularization, the array manipulation and character unpacking was strictly localized, and each other module essentially did its own thing. So one way to look at it is in thinking of composability as inversely proportional to the number of interfaces. It's also inversely proportional to the number of data types. This may be a little counterintuitive, but imagine that every module you had an absolutely unique interface and an absolutely unique set of data types. How much could you recompose that set of modules? Essentially, no recomposition is possible without writing new glue code to translate from one interface to another interface or to map one data type to another data type. So we come to uncoupling. This deals with orthogonality as separation of concerns, where we're going to look for high internal cohesion, low coupling, little overlap in functionality, so not much of that functional coupling, and we're going to look for high levels of information hiding and decision hiding. I'm going to walk through a little bit more of an extended example, which I have borrowed from Simon Brown's c4model.com. This is a component view where the items inside the dashed line represent a batch process running as a Windows service, so the container is a Windows service, And they're collaborating to compute a risk report and deposit it in a file system by a particular time of day. Now, we don't have the implementation details when we're looking at this view, but we can still glean some information from it. And in particular, I'm going to look for what areas I want to spend more time investigating and more time modeling or working on, because they present higher areas of risk, particularly with respect to coupling. So as I look at this, a few examples, or a few areas sort of call themselves to my attention. We have a risk calculator down in the lower right that the orchestrator invokes, and then the report generator needs to consume the output from the risk calculator in order to generate the report. So there must be some shared knowledge between those two components. We have two data importers here. We already looked at the external connection from one of them. But if we have two data importers that are both talking to external data systems, there may be some similar implementation that would represent some functional coupling between them. We have this report checker that says that it checks if the report has been generated by the appropriate time and raises an alert if not. The report checker is presumably looking at the file system to detect the presence or absence of a report. The report distributor deposits that report in the file system, so somehow those two things need to know that the report checker is looking in the same place that the report distributor is going to put the report. So there must be some shared knowledge between them. It's not represented anywhere in this diagram, so it could be latent coupling between those two modules that will come as a nasty surprise when I have to change the file system layout later on. And this orchestrator certainly sits in the middle, interacting with a lot of different interfaces and a lot of data types. So I probably expect to find a lot of transformation code in there, bridging between these different pieces. What can we do about some of these? I'm going to zoom in on this connection between the risk calculator and report generator. So this is a kind of semantic coupling between them. They have a shared data structure that they need somewhere. So depending on what our architectural style is, I might decide I need a standard or a schema as an external artifact. These are all written in C# inside the same service, so an external artifact is probably not appropriate. But instead, I might say I'm going to create a shared library to define the interface. That library may just define the interface only. The risk calculator can create an instance that implements that interface. The generator can consume anything that implements that interface. And so I've effectively represented that latent coupling in the form of this artifact. Another one of our problem spots, the data importers. We've likely got redundant implementations in there. And so I can certainly do some factoring out to get a library that would represent those common behaviors. I may eventually take it all the way to being a framework with an inversion of control that would invoke the importers, but I think my first step would be to say, I'm going to create a module that both of these components will use. And then we get our nastiest example up here of the latent coupling about file system layouts. In this case, I would probably create a module that would isolate the idea of the file system layout and represent it so that it would be consumed by both the distributor and the checker. Now, these solutions may have all sounded pretty similar. They all used libraries to represent something and weaken that form of coupling. But they used them in different ways. So one of them was defining a meeting point, an interface, so that I wouldn't have the semantic coupling between those two components, or at least the semantic coupling would be visible. I also used it to reduce the functional coupling between those two data importers. And I used it to isolate latent, implicit coupling in terms of the file system layout, so that's a decision hiding thing. Now, I do want to say that all of this is based on not seeing the implementation, so it's possible that any of these would be actually obviated by implementation techniques. But again, they're places where I'm going to go and look and spend more time and do more work with those areas. Another thing that I often find is that when I'm looking at the components and the runtime structure, that I want to think about modules to solve problems with components. Or if I'm looking at the module structure, maybe I can apply components to solve problems in the module structure. So don't get stuck in just the view that you're looking at or the perspective you're looking at. Sort of rotate it 90 degrees and see if there's another way to approach the same problem by applying more of the tools in your toolkit. When I'm looking at data, I think about code. When I'm looking at code, I think about data. But maybe that's because I'm working in a Lisp and they're kind of the same thing for me. Very often I'll find places where something that appeared to be totally different classes could actually just be instances of data of some other type. Elevating the level of abstraction that way is a way of uncoupling things at the functional level, so I no longer need to repeat myself in different layers of an application. And it can also make things more composable by narrowing your interface. So instead of having a dozen entity types being represented on your API, maybe you only need one or two if they carry along some extra data about where they came from or what they will do downstream. Definitely do use all of the tools you have in your toolkit. So modules, the layout of your code and libraries is one. Components is another tool you have. Increasingly, components and runtime processes are sort of isomorphic, but they don't always have to be. It's okay to run a couple of things together sometimes. And wherever we can find similar interfaces and similar data formats, we gain leverage. And so not every interface needs to be a one-off. That gets you minimal composability and maximal coupling. So just to recap, coupling determines your degrees of freedom. It enables some movements, like the knee or Watt's linkage. It inhibits other movements, like the knee or Watt's linkage. And it connects effects from one place to another. Coupling is necessary, otherwise we'd have a pile of bars on the ground instead of a steam engine pumping water out of a coal mine. But it can also prevent us from moving in ways that were unforeseen. We have different kinds of coupling, and it's useful to separate them and think about them differently because the tools that solve one may actually increase a different kind. And as you're working at this, hide the decisions where you can. Figure out which degrees of freedom matter for your system and which are likely to matter. Watch out for those semantic polymers. Find places where you don't need to propagate concepts throughout your enterprise. Use both your static and dynamic structures and try to find more instances of fewer interfaces. Of course, always prefer explicit to tacit. And remember that coupling really is everywhere, and our work is uncoupling where we can and providing the right motion where we need to. Thank you.
In the beginning, when you mentioned that component accessing a database, and then you move on to a REST API, and then on to a message broker. So REST operates on top of HTTP, which is a standard. You can use it from VBA, from the command line. And message brokers sometimes bring you some vendor lock-in. You need to use their API on receiver side, sender side. I don't know if I got correctly the idea of development coupling, but I was thinking that a REST API, with that respect, would have weaker coupling than using a typical message broker. Does that make sense?
Yes, it does. The way that I'm describing development coupling is that both ends of the interface need to change at the same time. What you're describing is more like the cost of change or the difficulty of moving away from a particular implementation, which maybe I'll add as another form of coupling for a future iteration of this talk. In terms of the REST interface, if I change the provider of the API, I do have to change the consumer, at least in some ways. Now, there are kinds of changes I can ignore. If you add extra data to a JSON format, and I'm not just trying to map that into an object, I'm actually looking for specific keys, then I don't care you've added extra data, and so that particular change is okay. But there are other changes you can make, like changing the cardinality of something that you nest, where I definitely have to change my end of it. The reason that the message broker has lower development coupling is because the format of the message as sent isn't necessarily the format of the message as I receive it. And so I have a mapping layer in the middle, which I can use to isolate myself from some of the changes upstream. And so the development coupling is, again, weaker than it would have been with the original SQL call.
Hi. Is there a lower bound on decreasing the coupling? So if I think about like pipe and filters on the Unix command line, sometimes by having a really simple data type, I have a series of characters going from one to the next, I end up having the things that are downstream trying to reinterpret the things that are upstream. So if the first command is like ls and there's columns of things, the next one has to try to use some other tool to recover the data type that was latent and sort of like decayed as it went through. So I was wondering, how do I reason about like how have I gone too far, or have I gone too far?
Yeah, thanks. That's a fantastic question. The problem with the Unix pipes and filters is not that they went too far in reducing the number of data types. I think one is a great cardinality for the number of data types in a pipeline. The challenge there is that they went to the least common denominator for what that data type should be. So their data type is character. And so the pipeline is stream of character. Imagine instead if the one data type you chose for pipeline were record in a CSV representation. You could imagine stringing together things that consume CSV records and emit CSV records. Unix pipes don't allow that, and so we end up trying to reconstruct our way to higher level data types. They went to the least common denominator because they wanted the widest possible array of programs that could work with it. If you're working in a restricted set of programs working with it, then you can go to the least common denominator data type that all of your pipeline components would share. So I still think one is a good answer, but character may not be the right type.
Probably one silly question. Do you think coupling is a technical debt?
Do I think coupling is technical debt? No, absolutely not. I'll elaborate a little bit. Like I said, coupling is necessary to get anything done. So there's a certain degree of coupling which just allows your programs to work. If you're in a microservices environment, you obviously have to be making calls across a network, so you have to share some representations. If you're all talking HTTP, you all need some functional coupling to HTTP libraries. And so it's both unavoidable and necessary. The kind of coupling that I represented at the beginning with the world falling apart around you is the excess coupling. It's the unnecessary coupling, the incidental, the latent coupling. Those are the ones that are problems. I'm not comfortable labeling everything we don't like as technical debt. I think there's a more precise usage of that metaphor, which is more about things that we chose to take on in order to achieve some other goals. But I will say excess coupling and particularly latent coupling will impede your rate of change.
One last question. So I teach microservice design, and I spent quite some time talking about service loose coupling as a design principle. And we talk about different types of coupling, not exactly the types as you mentioned, but I tell people that it is important to enforce positive kinds of coupling and avoid negative kinds of coupling. So we talk a lot about loose coupling versus tight coupling. So out of curiosity, and these are kind of common terms if you look at modularity and other literature, you didn't mention loose coupling, tight coupling. Do you think differently about these terms, the qualifiers that are kind of typical? You mentioned coupling versus uncoupling.
That's very interesting that you picked up on that. It's hard sometimes to hear the things a person doesn't say. I deliberately did not say loose coupling or tight coupling because usually if you look at it and you say, well, what makes that loose or what makes that tight, it devolves into one of those other 4 dimensions. And sometimes people just use loose coupling to mean something I don't like, or sorry, something I like, and tight coupling to mean something I don't like. So I tried to create this taxonomy as a way that we could look at different aspects of coupling and evaluate their relative strengths.
All right, let's thank Michael Nygard.